Okay, getting back to where we left off with our last example here, we had this situation where we tried to do our direct evaluation and we wound up with a 0 over 0 situation. And so using L'Hopital's rule, if we were to differentiate both top and bottom, and we do the derivative of cosine, we know that's negative sine x, and then on the bottom we'd have 2x. Now, notice what happens when we do that this time. If we put a 0 in here and a 0 over here, we still have a 0 over 0 situation. So in fact, L'Hopital's rule didn't really do us any good, I suppose. But here's the good news, is that L'Hopital's rule in what we call a stronger form states that we can continue to do this differentiation process until we get an answer, and therefore we will just do it again. And if we do our derivatives once more, we get negative cosine x here, and we get 2 here. And now, when we put a 0 in there, cosine of 0 we know is 1. We get negative 1 on top, 2 on the bottom, we get our answer, which is negative 1/2. And again, all of which can be verified by graphing the original function, showing that around 0, we're at negative 1/2 for our y values on both sides. So that technique is what we call the stronger form of L'Hopital's rule. And again, it just allows us to, if we try L'Hopital's rule and it does not work, because we still get an indeterminate form, okay, we can do it again until we don't have a determinate form, and then we can actually come up with a number. Okay. Now, I want to look at another one where we use that stronger form. If I were to ask you to find the limit as x approaches infinity this time of, let's say, 5x squared minus 5x over 8x squared minus 3. Well, if we put infinity into the
Noah
top,
Beacons, please report to the main office. Noah Beacons, report to the main office.
we're going to get infinity, and if we put infinity in the bottom, we're also going to get infinity. So notice that this is a little bit different form. It's not a 0 over 0 form. Okay, it's an infinity over infinity's form, but this is also another indeterminate form. So this is the second that we've seen. And therefore, the question is, can we use it? Can we use L'Hopital's rule? The answer is yes. Okay. Any of the indeterminate forms that we're going to be discussing, they can be dealt with using L'Hopital's rule. Okay. Now, we also know that there's a way that we could find the answer to this where we want the limit as x approaches infinity of this. All we're looking for here is the end behavior. And we know that what we learned in algebra, pre-calc, etc., is that if we take the, if we divide each of the top and bottom by the highest powered term here, if we do 5x squared over x squared minus 5x over x squared, and we do 8x squared over x squared minus 3 over x squared, and then we simplify, our new argument becomes 5 minus 5 over x, and then at the bottom we'd have 8 minus 3 over x squared. And if we took the limit as x approaches infinity, we know that anything with an x on the bottom, if this grows and this grows, that these are going to go to 0. So the answer here is 5/8. Okay? So that was the algebra technique that we learned to be able to find a limit at infinity of a particular rational function. And we also, generalize that to if we have the same degree on top as we do on the bottom, then ultimately that this is going to go to at infinity, it's going to go to whatever the leading coefficients are, top divided by bottom. So 5/8, we could pick that right straight off the equation from the first place. Now, just to illustrate that that you don't have to have that technique to be able to come up with an answer for this, we can use L'Hopital's rule. If we do the derivative of the top above, we're going to get 10x minus 5. And so this will be our way 1, this will be our way 2, L'Hopital's rule. And this will be 16x minus 3. And you'll notice that if we try to put our zeros or our infinities in here, we're still going to get an infinity over infinity form, which means that it's still indeterminate. And so if we differentiate again, we're going to get 10 over 16, which of course is 5/8. And so therefore, by L'Hopital's rule, the stronger form, we also get 5/8. And that would be the answer to this. This would also describe the end behavior of this function and so on. So it works out real nicely with rational functions because we've had a lot of experience with those type of functions, so we can show that in either way, very easily, we get 5/8 in this particular case. Okay. The problems that we're going to be working on today are going to be ultimately similar to this. We're going to be using L'Hopital's rule to determine limits. Again, first recognizing that we have one of the two indeterminate forms that we've discussed, either the infinity over infinity or like above the 0 over 0 case. And then we may have to use L'Hopital's rule once, or we may have to do it twice, or maybe 3, 4, 5, 6, 7, 8. Probably not going to be that many, but ultimately we can do it as many times as necessary to get ourselves down to an answer that is viable.